Okay, let's unpack this. You sent over a document that it's incredibly strategic. It's called the Intelligent Connected Safety Technology Roadmap,
Mm,
or ICSTR 3.0.
right.
And this isn't just some basic regulatory filing, it's a full-on national blueprint. I mean, it reads like a deep strategic consulting report, like something from McKinsey almost. It's defining the security architecture for smart vehicles for the next, what, 2 decades?
It absolutely operates at that strategic altitude.
Yeah.
And you're right to frame it that way because what this roadmap does is it moves safety from just being an engineering problem in one department.
Yeah, a line item.
Exactly. It moves it to being the foundational strategic priority for the entire industry's development. This latest version 3.0, it explicitly recognizes that safety has completely transcended just the vehicle's tech.
So it's bigger than airbags and crumple zones now.
Oh, much bigger. It's
Yeah.
now defined as the critical enabler for any kind of massive commercialization of autonomous tech.
Hmm.
And it's even framed as a key part of national security and economic vitality. It's that serious.
Hmm. Okay, so our mission for this deep dive is pretty demanding then. We need to cut through all that strategic language and really extract the core stuff.
Yeah.
The current technological status, where the big development trends are headed, and this is the key part, those very specific quantitative milestones for 2030, 2035, and 2040.
Right.
We're basically giving you, the listener, the executive summary of the next 2 decades of vehicle safety strategies straight from this core document.
Exactly. And the source makes a really crucial point right at the start about this strategic shift. It says the boundary of safety has fundamentally expanded.
What does that mean, the boundary?
It means we're no longer just talking about the car or even the driver.
Hmm.
The focus now is on the entire ecosystem. Vehicle road cloud. You'll hear the term V2X a lot.
Right, vehicle to everything.
Precisely. And the document brings up this concept, the bucket effect, which is a classic idea in risk management.
Okay, what's that?
It just means that the overall safety of the system is defined by its weakest link. It doesn't matter how good one part is if another part fails. So to hit these goals, you have to look beyond the car and mandate full industry and life cycle coverage. It forces system-wide thinking.
That bucket effect concept,
Yeah.
that's the ultimate accountability check, isn't it? I mean, you could have the most flawlessly designed autonomous car on the planet.
Sure.
But if the cloud platform that's pushing its software updates gets compromised, or a little roadside communication box at an intersection fails at the wrong second, the whole system's safety just collapses.
Precisely. The integrity is gone.
Mm-hmm.
And it's that systemic approach that drives the sheer complexity of the roadmap we're about to get into.
All right, let's start with the architecture itself. The ICSTR 3.0 completely rethinks the old view of safety engineering. It breaks safety down into 4 key interlinked subtopics. These are the first layer of the whole technical architecture. So what are these 4 pillars that the industry now has to master all at once?
These 4 pillars really represent the new frontier of risk management for these vehicles. They reflect the new reality that when you add software, AI, and connectivity, you get entirely new ways for things to go wrong.
Okay, so pillar number 1.
The first pillar is the bedrock, functional safety, or just FS. This is the traditional foundation of automotive safety. It deals with risks that come from actual failures of components.
So things breaking.
Right. Specifically, random hardware failures, a chip overheating, or systemic software faults, like a known reproducible bug in the code of an electronic control unit. This is the world of established standards like ISO 26262.
So functional safety, or FS, is basically asking the question, did the machine break?
Correct. Did the circuit short out? Did the code do something wrong because of a flaw that was baked in? It's the oldest and most understood safety domain. But as cars got smarter, a huge gap opened up.
And that leads to the second pillar.
That leads us to the second pillar, expected functional safety, which is almost always called SOTIF.
And this is where it gets really, really interesting, because SOTIF is about failures that happen even when nothing is technically broken.
Exactly. SOTIF is all about the uncertainty that comes with using AI in a dynamic, messy, real world. The risks here come from performance limitations. The system is working perfectly as designed, but the design just isn't good enough for a new, weird situation it's never seen before.
Like an AI getting confused.
Right. Uncertainty in the AI algorithms, or just a super complex, unforeseen operating scenario. Think about the system misinterpreting a unique combination of shadows on the road, plus dust in the air, plus a weird light glare. Nothing failed, but the perception was wrong.
I've heard a good distinction. FS asks, did the system break down because of a hardware or software bug?
Yeah.
Whereas SOTIF asks, did the system fail to stay safe because the AI failed to understand the situation? even though every single component was working perfectly.
That is the perfect distinction. SOTIF is fundamentally a problem of scenario complexity and AI trustworthiness. It's a massive challenge.
Okay, so that's two. What's the third pillar?
The third is information security, or what we all call cybersecurity. These are the external malicious threats. As the car basically becomes a mobile data center that's constantly connected to this V2X ecosystem, the whole threat profile changes.
It's a target now.
A huge target. So this pillar covers remote attacks, someone trying to seize control of the vehicle, data leaks, privacy violations. These threats go from being a digital problem to a potential kinetic hazard if someone compromises the car's controls.
And that brings us to the fourth and final pillar, the one that really defines this roadmap as version 3.0, Converged Safety or Fusion Safety.
This new pillar is by far the most ambitious. It addresses the systemic risk that happens when the other three dimensions, FS, SOTIF, and InfoSec, stop being separate problems.
And they start to, what, interact?
They start to interweave, overlap, and influence each other in real time. It's about the conflicts between them.
Can you give us an analogy for what a converged safety risk would actually look like in the real world?
Certainly. Think of it as Murphy's Law for smart cars. Let's say a car system gets a malicious remote command. That's an InfoSec risk.
Okay.
Now, that command doesn't actually take over the car, but it forces it into an emergency low-power state. That, in turn, leads to temporary sensor degradation. Now you have a SOTIF risk because the sensors aren't performing as well.
I see the chain reaction starting.
Exactly.
Huh.
And now, that temporary sensor degradation exposes a known but previously non-critical flaw in the hardware's fail-safe routine. That's an FS risk. All three just cascaded.
Wow.
Converged safety is about designing the system to manage that cascading multi-domain paradox. You have to resolve those conflicts. You have to make sure that a safety mechanism for one pillar, like, say, aggressively shutting down a system because of a cyber threat, doesn't accidentally create an even bigger hazard in another domain, like causing a loss of control.
That completely changes the job of a safety engineer. They're not just debugging code anymore. They're solving these dynamic multi-domain paradoxes.
That's it. It forces a totally holistic view of the safety lifecycle.
So we have the 4 pillars, which is layer 1, but you said it's a 3-layer framework. Can you just briefly outline the other 2 layers so we know what's coming later?
Sure. Layer 2 is the implementation layer. It's the how you do it. It defines the core engineering processes you need to actually achieve safety in those 4 domains. And it's broken into 3 activities that span the whole vehicle lifecycle.
Which are?
Safety development, which is all the early stuff design, modeling, risk assessment. Then testing and verification, which is simulation, physical tests, proving the design works. And finally, operation safety.
And that's after the car is sold.
Right. That's the continuous real-time monitoring, threat detection, and emergency response for the car when it's out on the road.
Okay, and all of that, layers 1 and 2, they rest on the final layer, layer 3.
That's right. Layer 3 is the 4 foundational supports. These are the infrastructure pieces that let the whole system function and improve over time. They are databases like failure mode libraries, toolchains, the software you use for design and analysis, standards and regulations, the rule book, and finally, safety certification.
The whole 3-layer structure really reinforces that systematic consulting report approach we talked about.
It does. It's incredibly thorough.
Okay, so before you set aggressive goals for 2040, any good strategic report has to rigorously assess where you are right now, the status quo. So let's dive into where the system stood as of 2023 across these 4 pillars, especially comparing domestic progress against the big international automotive players, Europe, the US, Japan, South Korea.
This benchmarking is absolutely critical because it provides the context for the whole roadmap. It shows you exactly where the gaps are that need to be filled. It's the "you are here" map.
Let's start with the first one, functional safety, FS. The assessment here is following, catching up.
Right. So not leading, but not hopelessly behind either. They're in the race, but they're chasing the established powerhouses.
So what's the progress they've made that even puts them in that following category?
A lot of it is about formalizing the rule book.
Mm-hmm.
They've established a national FS standard, the GBT 3459 RADO 2022 series, and it's quite comprehensive. It covers everything from power batteries and drive motors down to the individual chips.
So the paperwork is getting sorted.
The paperwork and the processes. The rate of organizational certification is accelerating incredibly fast. The source notes that certifications in 2023 nearly tripled from the year before. So industry process maturity is growing very quickly.
But if they're accelerating that fast on standards and process, why are they still rated as following? Where is the real structural gap?
The gap is in the foundational infrastructure for quantitative assessment. When you get to sophisticated FS analysis for the whole vehicle, not just one component, safety analysis is still too reliant on qualitative expert experience.
On gut feelings, almost.
A very educated gut feeling, but yes, on subjective judgment. They lack the deep, robust accumulation of foundational databases. We're talking huge, high-volume libraries of detailed failure modes, and the tools you need to support a truly quantitative, numbers-driven, whole-vehicle safety assessment.
And that quantitative approach is standard practice elsewhere.
In the established strongholds, yes. It allows for highly predictable risk modeling. Without those massive databases, your assessment remains more of an art than a scalable science.
Okay, let's move to expected functional safety, SOTIF. The assessment here is much more optimistic, which is surprising. It's basically synchronized.
It is surprising. It suggests they believe they're on par with international efforts, which is a big deal given how hard SOTIF is for everyone, everywhere.
So what's their strategic edge here? The document mentions a Chinese characteristic approach. What does that mean?
It means they're leaning heavily on their ability to build out centralized infrastructure. They're using the V2X ecosystem, that vehicle road cloud collaboration, as a core part of their safety strategy to manage risk.
So they're not just relying on the car's brain.
Not at all. They're building a three-layer protection architecture: prevention, pre-control, and prediction. The infrastructure, the roadside units, the cloud platform, they all help provide early warnings and collaborative decision-making. It mitigates the inherent uncertainty you get from any single AI agent trying to figure out the world on its own.
That's a fascinating way to tackle the SOTIF problem, using connectivity itself as a safety redundancy layer. But what's the fundamental technical challenge that still exists for SOTIF, not just for them, but, well, globally?
It's still the core theoretical problem. There is no unified, clear definition or methodology for quantifying SOTIF risk. It's not like functional safety where you can calculate the mean time between failures.
Right.
With SOTIF, you're trying to put a number, a risk percentage, on the chance of an AI misinterpreting a weird mix of shadows and dust. It's probabilistic, it's complex, it's sometimes just chaotic.
And are there infrastructure gaps there too?
Yes, a very specific one is called out. A lack of domestic high-fidelity, closed testing facilities that are needed for SOTIF verification.
And we're not just talking about a simple test track here, are we?
No. We're talking about highly controlled environments, almost like a movie studio, that can reconstruct the environment with incredible fidelity. You need facilities that can recreate those super rare specific triggering conditions that cause SOTIF failures, heavy rain at a certain angle, specific fog densities, weird and complex lighting.
And without those, you're just driving around on the street hoping you see it.
Exactly.
Yeah.
And even where they have sophisticated simulation tools, a core unsolved problem is the trustworthiness of those simulations, the confidence level. You have to be able to prove that your virtual world results directly correlate to the real world's physics. Otherwise, you can't use it for safety certification.
Okay, next up is information security, InfoSec. Here, the status is judged as clearly lagging, still needing to catch up. But wait, the source also says there have been strong advances in core tech security encryption, intrusion detection systems, security operations centers. Those all sound like cutting-edge technologies. So why is the overall status still catching up?
That's where you see the difference between having a technological capability and having systemic maturity. The tech is advanced, you're right. But the key gap is in the speed of standardization, regulation, and the sheer scale and maturity of mass application across the whole industry.
So the tools exist, but they're not everywhere and the rules aren't set.
Precisely. International strongholds have more mature and comprehensive security management systems, policies, and frameworks already in place. The roadmap is very explicit that integrating with international security standards is paramount. So it's more of an integration and governance deficit than a pure technology one.
Finally, we get to the newest pillar, converged safety. Since this is a new field for everyone, the status makes sense. Starting phase methodology exploration.
Right. They're pioneering it, but that also means they have the steepest learning curve.
So what's the initial focus for them right now? Where are they starting?
The current industry focus is on internal integration. So primarily integrating functional safety and SOTIF. There's also some very early foundational work on linking FS and InfoSec analysis.
They're trying to build the first bridges between these domains.
Exactly. The document highlights that as V2X deepens, the characteristics of these complex infophysical systems become dominant. That means these multidimensional safety issues become really tightly coupled, and they influence each other.
And what's the main strategic gap holding this exploratory phase back?
It's fundamental. The industry just lacks a mature systematic theory. It lacks a clear set of methodologies, and it lacks the tool support you'd need for multidimensional fusion testing and design. How do you design an FS hardware failsafe that can handle the performance hit from a cyber attack? The tools and the science for that kind of systematic modeling just aren't there yet. Not for them. Not for anyone, really.
So we've seen the gaps. Reliance on expert experience in FS, the huge quantification problem in SOTIF, the standardization lag in InfoSec. If the ultimate ambition is really zero casualties, zero accidents by 2040, they need some incredibly aggressive, quantifiable milestones to bridge that gap.
And this is where the ICSTR 3.0 really shifts from just being an assessment to being a strategic mandate. It gets very, very rigorous with its metrics.
It sets 3 core metrics, right? Broken down across 3 time horizons, 2030, 2035, and 2040.
Exactly. Near term, midterm, and long term.
So let's start with the most critical one, the one everyone can understand. Accident interval mileage for accidents caused by the intelligent system itself. This is basically a measure of risk acceptance.
It is. It directly answers the question. How far, on average, should a fleet of these vehicles be able to travel before an incident happens that was the intelligent system's fault?
So what's the goal for 2030? This is the near term, the baseline for getting L3 and L4 autonomy out there at scale.
The goal is tough. For high-speed environments, like highways, it's 1 million kilometers per incident. For city environments, it's 500,000 kilometers per incident. This is the first time we're seeing a hard, public line drawn in the sand for system safety performance.
And how quickly does that safety margin have to improve by the midterm, by 2035?
By 2035, they're aiming to double those targets. It reflects growing confidence and wider deployment. So high-speed travel has to reach 2 million kilometers per incident, and city travel has to reach 1 million kilometers per incident.
That's a significant tightening of the safety envelope.
It is. It's moving towards a level of industry-wide trust in the systems.
Okay, and the final target for 2040, the trajectory towards zero accidents. You mentioned 10 million kilometers per incident. To really put that in perspective for everyone listening, how does that compare to, say, current risk levels for human drivers?
That 10 million kilometer goal is massive. To give it some context, the average driver in the US or Europe might drive maybe 1 to 1.5 million kilometers in their entire lifetime.
The whole lifetime.
The whole lifetime. So this 2040 goal is demanding that, on average, the intelligent system should only be responsible for an incident once every 10 lifetimes of human driving. It means system-induced accidents would become an incredibly rare, almost negligible event. That 10 million coincident figure is really a global benchmark for what acceptable risk looks like in a fully autonomous world.
To go from 1 million to 10 million in just 15 years, that's not incremental improvement. That sounds like a decade of engineering miracles they're planning on.
It is. It demands a paradigm shift in thinking, not just optimizing what they have now.
Okay, let's move to core metric number 2, information security compliance rate. This seems to speak directly to that bucket effect idea, the whole systemic defense.
It does. This measures the integrity of the whole V2X system. It's tracking the degree to which the entire network, the car, the road infrastructure, the cloud platforms, is complying with all the established security requirements and standards. It's about systemic integrity, applied consistently.
So what's the initial target for 2030?
It's an incredibly high bar right out of the gate. Industry average compliance must be greater than or equal to 90%. That means a preliminary V2X defense system has to be structurally sound and deployed across the industry at scale in just a few years.
And it climbs steadily from there, I assume.
It does. By 2035, the target goes up to 95% or more. The network needs to be nearly ironclad. And then finally, by 2040, the goal is near perfection. Industry average compliance of 99% or higher.
99%.
It's a hard number that signals just how high a priority they're placing on hardening that digital infrastructure. They recognize that without that, the mileage targets are simply unreachable.
And the third and final core metric, the maturity of the converged safety design and development system. This tracks how well they're integrating all 4 of those pillars.
Right, this is a system maturity metric. It asks, has the industry actually figured out how to design, test, and operate in this new converged risk environment?
So what's the first step by 2030?
By 2030, the goal is to have a preliminary converged safety design system built. And the initial focus will be on the highest risk, most connected parts. The intelligent driving system itself and the key V2X communication components.
So they're focusing on where the conflicts between safety domains are most likely to show up first.
Exactly. Then by 2035, the requirement expands. They have to build a basic system that covers all V2X critical systems, integrating the road and cloud infrastructure into the safety design process much more deeply.
And the final goal for 2040.
By 2040, they demand a fully completed system. This means full coverage of every element in the V2X system: vehicle, road, and cloud. It means ensuring systematic safety design integration across that whole ecosystem and reaching a state where all those potential multi-domain conflicts could be systematically identified, modeled, and mitigated before they ever become a problem.
Those overall goals are monumental. I mean, 10 million kilometers per incident, 99% compliance. It's a lot. So now we have to get into the tactical execution. We need to look at the specific 15-year plan for each of those 4 safety pillars across the 3 process layers: development, testing, and operation.
This is where the rubber meets the road. This is the granular plan for how they're going to invest resources and solve those technical gaps we talked about in part 2.
Let's start with functional safety, FS. The overall trend here is moving from just designing for the reliability of a single car to supporting the whole V2X integration and meeting the really tough requirements for full automation.
Right. The key shift is that FS is no longer just about component failures. It's about the failure of the connected architecture.
So what are the 2030 goals? It looks like they center on integration and technological autonomy.
They do. In the development process, the plan mandates that a preliminary V2X FS architecture has to be established. This means designing the safety architecture to account for the reliability of the communication link itself. For instance, the vehicle has to be able to degrade gracefully and safely if it loses its cloud connection.
And this is where that strategic challenge of toolchains comes in, right? The geopolitics of it.
Absolutely. The plan mandates establishing independent indigenous IP toolchains. This is a crucial strategic move.
Why is that so important?
Well, think about it. The software tools you use for safety analysis are core intellectual property. If you rely on foreign IP for that, you introduce 2 massive risks. First, supply chain disruption. Second, you might be using tools that weren't even designed for the unique requirements of a centralized V2X architecture. To get to that 85% or higher implementation coverage they want, you need domestically controlled tools.
And what about an operation once the cars are on the road?
There, the focus is on prediction. Key system failure prediction coverage has to reach 90% or higher. This is proactive maintenance. They have to build out those comprehensive V2X system failure mode and safety mechanism databases that directly addresses the lack of database accumulation gap we noted earlier. You can't predict failures if you don't have a massive data set of past failures to learn from.
And looking further out to 2040, what does the mature end state for functional safety look like?
By 2040, the development goal is near full coverage. V2X FS architecture implementation has to hit at least 95%, and the toolchains will evolve. The goal is to establish intelligent, converged, and autonomously controlled toolchains.
What does a converged toolchain do?
It means the FS tools won't just analyze hardware reliability in a silo. They have to be able to share data and interact dynamically with the SOTIF and InfoSec analysis tools.
And operationally?
Operationally, the target is near perfect failure prediction coverage for key systems, reaching 99% or higher. This implies the system can reliably predict and preempt almost all random hardware and systemic software failures before they ever cause a hazard. It's about preventative action, not just reactive fail-safes.
Okay, now for the really tricky one. The expected functional safety, SOTIF roadmap. This is the technical dark horse, the one dealing with all that AI uncertainty.
It is, and the overall trend here is developing a full process solution. It has to cover hazard recognition, real-time protection, learning from new events, and, most critically, testing. And we have to say it again. The roadmap itself acknowledges that the core obstacle is the lack of a unified way to quantify risk. The whole plan pivots on solving that theoretical problem.
Let's start with the ultimate quantitative measure for SOTIF, the accident interval goal.
The 2030 milestone sets the residual risk accident interval, so accidents caused by SOTIF issues, at 1 million kilometers per 100 vehicles in high-speed scenarios. This is really the first measurable target for AI trustworthiness in complex driving.
And what about on the testing side by 2030?
The goal is the preliminary establishment of high-fidelity, high-trust verification toolchains, specifically for standard scenarios. They're also pushing for 100% coverage and verifying all the reasonably foreseeable risk scenarios.
Let's pause on that phrase, high-trust verification toolchains. What are the specific technical hurdles you have to clear to be able to certify that a simulation is just as good as a physical safety test?
This might be the single hardest technical challenge in the entire SOTIF domain. Trustworthiness means proving that your simulation environment and the synthetic data it creates accurately represents the statistical distribution of real-world risks, especially those super rare, complex trigger scenarios.
You'd have to prove the virtual world is real enough.
Exactly. You have to validate the simulation's fidelity, its ability to mimic real-world physics, sensor noise, weather, lighting, is high enough that you can guarantee safety certification based on virtual results. This requires massive amounts of real-world sensor data and advanced physics models. And right now, there's still confidence gaps.
And what about the operations side for SOTIF in 2030?
Here, that V2X collaboration is key. By 2030, the V2X risk early warning success rate has to hit at least 90%. And the success rate in handling foreseeable risks also has to be at least 90%. This means highly reliable, real-time communication between the car and the infrastructure to manage potential SOTIF pitfalls before they turn into accidents.
Now, fast forward to the 2040 end state. How do those targets show that they've conquered this quantification challenge?
The overall residual risk goal for 2040 jumps to 10 million kilometers per 100 vehicles. That's the industry-wide benchmark for near-perfect SOTIF performance.
And for testing?
For testing, the roadmap demands the comprehensive establishment of high-fidelity, high-trust verification toolchains. That signals they expect to solve that confidence-level validation issue. And operationally, the success rates for early warning and handling foreseeable risks both have to be 98% or higher. The whole path is about turning that probabilistic uncertainty into manageable, quantifiable risk.
All right, on to the information security InfoSec roadmap. The trend here is shifting the defense perimeter from just hardening the car's computer to defending the entire cloud pipe device edge V2X network.
And using AI to do it. The trend is accelerated use of AI for intelligent threat sensing and automated response.
What's the 2030 development goal?
By 2030, the goal is pervasive security design. InfoSec has to be integrated into the design, testing, and operation lifecycle. A preliminary V2X defense system needs to be built, pushing that compliance metric to 90% or more. Security can't be an afterthought you bolt on at the end. It has to be designed into the core V2X architecture from day one.
And the operation milestones by 2030 look very quantitative. They're about the performance of the monitoring systems.
They are. They have to establish robust security operation capabilities. So continuous monitoring, warning, and rapid response, and build a shared industry vulnerability library and threat intelligence platform.
Let's really scrutinize those 2030 performance metrics for monitoring. They're targeting a security risk monitoring leak rate, so missed attacks of 5% or less, and a false positive rate of 15% or less. What does it technically take to get that kind of accuracy?
That requires extremely sophisticated AI-driven security operations centers, or SOCs. A leakage rate of 5% means you're only missing 1 in 20 attacks, which is already a very high bar in a network this big. But keeping the false positive rate low is just as hard.
Why is that?
Because V2X systems generate a mind-boggling amount of data sensor noise, routine communications, network fluctuations. The SOC has to be able to sift through petabytes of data and distinguish a real malicious anomaly from all that benign noise, and do it at network speed. You can't have the system constantly triggering emergency shutdowns because of false alarms.
And looking ahead to 2040.
By 2040, the development plan calls for the full V2X defense system to be completed, supporting both single-vehicle intelligence and network enablement. And compliance hits that near-perfect 99% or higher.
And the operational performance metrics must get even tighter.
They tighten dramatically. The leakage rate has to fall to 1% or less, and the false positive rate has to be 5% or less. This implies a nearly autonomous, highly accurate defense system that can practically self-heal and microsegment threats on the fly. You need that level of security to support large-scale L5 automation, where any single security failure could lead to a systemic catastrophe.
And that brings us to the final roadmap. Converged Safety. Fusion Safety. This is the most complex, most exploratory pillar of them all.
It is. The trend here is moving from just pure theory to actual technical breakthrough, solving those key conflicts between the security domains. And the challenges are huge. Not just the lack of standards, but the difficulty of modeling this complex dynamic risk. And then there's the economic challenge, the trade-off between achieving this incredible safety integrity and keeping costs under control.
So what are the initial 2030 goals? How do they even start to model these interactions?
By 2030, the goal is to build a preliminary fusion safety design system that covers intelligent driving and V2X components. And this initial system must allow their monitoring platforms to achieve a risk identification rate of 70% or more for these converged safety risks.
70% identification is a pretty ambitious start for a brand new field. What about on the testing side?
The initial focus is on collaboration. Preliminary multidimensional safety collaboration testing systems have to be built, with risk scenario coverage hitting at least 70%. And this isn't just testing FS, then SOTIF, then InfoSec one after the other. It means systematically testing the complex interaction points. For example, measuring how a necessary security patch update dynamically affects SOTIF performance in low-light conditions.
Let's dig into that dynamic conflict modeling. What kind of technical breakthrough do you need to actually model a conflict between security domains like that?
You need a multi-physics or multi-domain modeling environment. You need tools that can simultaneously simulate network topology, communication latency, physical sensor perception, and hardware reaction times, all in one go.
Can you give an example of a conflict?
Sure. A dynamic conflict might happen if the InfoSec system mandates a full system reboot because of suspicious activity. The FS system is designed to handle a hardware reboot, that's fine. But maybe the SOTIF system was never trained on the degraded operational mode the car is in during that brief reboot window. Modeling that requires a fundamentally new kind of simulation architecture that can integrate data from all four domains.
So the long-term vision for 2040 must be the full conquest of this complexity.
It is. The design system has to achieve full coverage of all elements in the V2X system. And the monitoring platform risk identification rate for converged risks has to reach 90% or higher.
That 90% identification rate for converged risks, that's basically the holy grail of systematic risk management.
It really is. And crucially, the testing layer will have achieved a full V2X fusion safety testing and verification system, with multidimensional risk scenario coverage also hitting 90% or more. This would mean that the industry has finally solved how to analyze, design, and verify risks that are dynamic, multidimensional, and often contradictory. It would turn converged safety into a mature, quantifiable engineering discipline.
We've laid out the massive technical requirements across all four roadmaps, but those targets are just unreachable unless you simultaneously strengthen that foundational infrastructure layer 3, the foundational supports. This is how they plan to close the gaps we identified at the start.
These four foundational pillars are the critical enablers. They're what turn the strategic roadmap into an actual reality. They directly address the deficits in standardization, toolchain sovereignty, and infrastructure.
Let's start with the first one, standards and regulations.
The source material is very direct about the urgency here. Because the technology is developing so fast, the industry has to accelerate how it formulates and refines security standards. The tech is simply moving faster than the rulebook.
And there's a specific strategic focus on making these national standards mandatory, especially for functional safety.
Exactly. Mandatory standards are needed to define clear security baselines and explicit quantitative metrics. Remember the bucket effect. If safety is defined by the weakest link, you need regulatory intervention to enforce consistency across the board. It stops the entire industry's safety level from being dragged down by a few low-adherence players.
And the regulations themselves have to change.
Dramatically. The oversight, covering product admission, testing, and operation supervision, has to become as dynamic as the technology it's trying to govern.
Okay, pillar number 2, toolchains and databases. This is where they address that reliance on foreign IP and qualitative expert experience. This shift to independent, intelligent toolchains feels strategic, almost geopolitical.
It's both technical and strategic. The mandate is to invest heavily in developing intelligent, fusion-capable, and autonomously controlled toolchains. The goal is unambiguous. Reduce reliance on foreign IP and secure technological self-sufficiency in core safety analysis tools. It's about national strategic control over the safety architecture.
You said fusion-capable toolchains?
Right. They can't operate in silos anymore. They need to be designed from the ground up to ingest and correlate data streams from FS failure models, SOTIF scenario libraries, and InfoSec vulnerability reports, all at the same time to support that converged safety analysis.
And what about the data that underpins all this?
Just as crucial is building and sharing industry-wide databases. This includes high-value assets like hazard and failure mode libraries for whole vehicles, detailed hazard scenario libraries to feed the SOTIF verification tools, and for InfoSec, shared vulnerability libraries and threat intelligence. These shared resources are essential. Without collective industry data, that quantitative risk assessment, especially the 10 million kilometer goal, is just impossible. It has to be a collective learning exercise.
Okay, the third foundation, testing and certification. This gets at that critical SOTIF infrastructure deficit. What does the roadmap specifically require to solve the high-fidelity testing problem?
The strategy mandates comprehensive, multi-level testing systems, not just for the final vehicle, but for the systems, the chips, the operating systems. But the key SOTIF solution requires very focused action, establishing dedicated closed test facilities, ones that are equipped to simulate those extreme specific triggering conditions we talked about. Combinations of rain, snow, fog, complex light with high precision. It's the only way to truly verify performance limitations in a controlled, repeatable environment.
And what about solving the reliance on virtual testing?
They need to develop robust, high-fidelity, virtual physical fusion testing methods, where simulation and physical tests are seamlessly integrated. And critically, they have to solve that foundational problem of improving the trustworthiness, the confidence level of virtual simulation tools. They have to ensure the simulation results are reliable enough to serve as evidence for safety certification. That's how you reduce the immense time and cost of physical validation.
And finally, the fourth foundational pillar, industry collaboration. This is the ecosystem approach, breaking down the silos between government, industry research, and the end users.
The roadmap mandates formalizing what they call the gov-industry research use, multi-level collaborative mechanism. Safety is a collective systemic responsibility, especially when the vehicle is relying on external infrastructure and cloud services.
And this collaboration has to be more than just paperwork.
Much more. It has to extend to formalized shared threat intelligence and rapid emergency response systems. Think about the implications of that 99% InfoSec compliance goal. In a highly connected V2X environment, if a vulnerability, a zero-day exploit, is discovered by one company, it has to be instantly shared and neutralized across the entire ecosystem.
Through over-the-air updates or other procedures?
Exactly, to prevent a widespread synchronous incident. This collective defense strategy really reinforces the idea that safety is no longer a proprietary advantage. It's a shared public good that's essential for the industry's growth. The focus is on collective accountability and rapid coordinated response.
This has been an incredibly detailed journey into this strategic planning document. So what does this all really mean for you, the listener?
I think the strategic shift is undeniable. Safety has moved decisively from isolated component protection to a quantified, systemic, and converged V2X ecosystem defense. The targets are just incredibly precise, measured in millions of kilometers and high compliance percentages. The shift is profound. It's moving from reactive safety protecting against known failures to predictive and proactive safety, especially in SOTIF and Converged Safety. The source material makes it very clear that the industry has to aggressively tackle the most complex challenges, quantifying SOTIF risks from AI uncertainty and systematically resolving the deep conflicts in Converged Safety before high-level autonomous driving can really scale globally without taking on undue risk. The whole plan is designed to turn chaos into quantifiable risk.
It's a challenge that crosses engineering, infrastructure, regulation, and even national industrial strategy.
Absolutely. Which brings us to a final provocative thought for you to mull over. We've seen these quantitative goals, 10 million kilometers per incident, 99% compliance by 2040. If the pace of technological innovation, particularly in AI, continues to outstrip the pace of standardization and regulation, which the source suggests is happening right now, how does the industry ensure this rapid, almost unprecedented climb to zero accidents doesn't inadvertently introduce some new kind of catastrophic, high-scale, unforeseen risk that are existing and still incomplete methodologies for converged safety can't yet predict or contain?
In other words, could the very speed and complexity of the V2X system, while enabling all this safety, simultaneously generate new categories of risks that are even harder to model?
That's the question.